Alright, hell yeah. So what we're going to go over today is bad integration. And we're going to do the volume of a sphere. You know what I mean? What is the volume of a sphere? Isn't it like 4/3? Pi r cubed. You know what I mean? It's a volume. It's got to be in units of like meters cubed. So at least we know that. Okay, hell yeah. So now what am I talking about bad integration? You know, integration is all about, hey, trying to take... I mean, it would be like this. If I have a circle, and then I wanted to chop it up into squares, you know what I mean, and then add up the squares, well, that's kind of a form of integration. I got 1, 2, 3, 4, maybe 5, 6, 7, 8, you know what I mean, maybe 9, you know what I mean, 10, and the rest are just like finishing this. Anyway, so that's kind of what we're doing. So we're going to take a sphere. Oh, shoot. Alright, hell yeah. Okay, so we're going to take a sphere and, so I was just thinking, if we have a sphere, what we're going to do is like, hey, divvy it up in two. So here's kind of the split down the middle, and here's this direction. And what I thought is like, hell yeah, let's take a slice like this. You know what I mean? If this is really thin, like what does this look like? It looks like a triangle. So I just visually I thought this looked like, you know, a rectangle where you would have, you know, just like, you know, there you go. So it's like a rectangle. So like what would the area of this be? Well, it would be that same rectangle, like full thickness. It would be, I mean, I'm sorry, what's the volume of this? Well, it would be the volume of that full rectangle divided by 2, because it's sliced, you know, it's perfectly sliced, you know, kind of down to the 2. So if I slice this in half, I'd have 2 of those. Okay, so that's kind of the concept I'm getting at. Is just like, well, this looks like, so for just the half, it looks like a half a slice. And so the concept that I'm getting at is if you did kind of 2 of those, so you know what I mean, 1 over here as well, then you know what I mean, you'd have 2 of those slices. And then if you finish it off like this, I would say that this slice is equal to that slice is equal to that slice is equal to that slice. So what I'm going to say is, I don't even know if this is going to work out. Oh, no, this is perfect. This is perfect. No, this is how I did it. So if I take it right at the middle, you know what I mean? So right at the middle, this is a full radius, you know what I mean? This is full diameter. And so, and then, you know what I mean? I guess I know enough integration, because we're trying to do this from the perspective of like, well, let's say you didn't really know integration well. You know what I mean? I want to do these same things for like differentiation, but we're doing integration. It's area under the curve. You know what I mean? Or double the integration, you got area and volume. Okay, so so I do know that this is d theta. I guess I at least know that. We're like, hey, going up, or you can just say some theta. But anyway, oh, and then the other thing that I know, let's say it is an angle. I do know if this angle is really small, and we have this angle in radians, which just seems mind-melting, the concept of radians. But all a radian is if we have a circle, there's the radius, and guess what? If we made this into a string and draped that string up this circle, we'd get to there. And so this is the angle of 1 radian. And that angle of 1 radian kind of marks out 1 arc length. So what I do is radians times radius is something normal, and the normal thing right here is what we call S, and this is the arc length from there to there. Cool. Alright, so, but I do know if radians is really small, oh, do I even need to know that? I kind of forget how I did this one, but, oh, whoa. No, I think I just did d theta. I at least know enough about integration that if I get an integration of, you know what I mean, whatever, d theta, then all I have to do is integrate from 0 to 2 pi. You know what I mean? Sweep all the way around. If I know the area of this slice, then I'm going to add up all the slices all the way around 360. You know what I mean? So hell yeah. And let's say I don't even know how that works. You know what I mean? Let's say that's magic trickery to me. That's fine. At least I know the concept works. You know what I mean? So I'm at least solid enough when I go do the integration of d theta to get theta. I'm like, you know what I mean, totally satisfied. And then we'll evaluate it at 0 to 2 pi. And so we're going to throw in 2 pi minus 0. And hell yeah, we'll have 2 pi, you know, times, you know, something. Okay, so going back to here. So what is the volume of this slice? You know what I mean? I guess we have d theta there, and I guess I'm at least comfortable and confident knowing that, well, that's going to be in there, and that's kind of what we're going to integrate. So I really don't have to worry about this. You know what I mean? That's still kind of bizarre to me, but all I have to worry about is like, hey, what is the volume of this? Like, let's say, what's the volume of this whole thing? Well, the volume of this whole thing is real easy. It's just diameter d theta, or 2 times the radius, 2r times d theta. That is, and this is in meters, and I'm going to say that, oh, see, I already kind of messed up, Wouldn't this be ds? You know what I mean? Didn't we just define arc length as that? And theta is just an angle. Oh, that's what I was trying to get at. I was trying to get at this, is that if I do know the radians, well, oh man, see, now I'm bumming myself out. But yeah, I guess I kind of proved that no, your units have to match. This has to be in meters. This has to be in meters. So let's stick with ds, and then we'll probably, oh perfect, and then we have an equation. Let's say this is arc length, and we're just calling it s. Sometimes doing things with like ds, dx, like that's where it gets confusing. I'm just gonna say it's s. I'm just gonna say it's the friggin' arc length, and that's the angle. Well, we just defined the arc length as the radians. This s is radians times radius. So let's do that. Radians, theta, r is equal to s. So even just taking away the d really helps me out. It might help you out too. So now that we know this s is theta r. So cool. But we really do know it's d theta. So we'll have d theta r is equal to s. But actually getting the normal equation, I consider this normal and this mind melting. Anytime I see a d, my mind's going to melt. But anyway, so hell yeah. So we figured that out, and now we're rocking and rolling, because now we know that the volume of this whole thing, and again, we're doing bad integrate. We're going to get the wrong answer, but it's going to be close. So that's kind of the take-home message. All right, now let's do it. So the volume of this is going to be 2r times s. Okay, that's the volume. And now we're good to go. You know what I mean? Oh, no. We're not good to go, because we wanted to take this one slice. Totally forgot about that. That one slice is only right there. So it's only a quarter of it. The reason why I did 4 and I could see that geometry is that was like the aha moment. Hell yeah. I can, but I do know there's something fishy going on about this. This is not that. You know what I mean? And I get it. I have a subtle hint that I'm not going to get the right answer, but it seems like it's hella close. You know what I mean? If I have a ds right here, and it almost looks like that. Close enough that hopefully we get pretty close, and we're going to do our percent error. We'll at least do the percent error calculation. Okay, so then I know that if this is the volume of that whole thing, it's just divide by 4. So now I have the volume of this slice is rs divided by 2, and then I know that s is theta r, so we're going to go r theta r, you know, make it totally obvious. Cool, and now we're going to say the volume of that slice is 1/2, and obviously this theta is d theta for this, and so we'll go 1/2 r squared theta, and now we'll make it look like that. You know, 1/2 r squared d theta makes sense to me, and now we have to integrate from 0 to 2 pi. And guess what? Integration is super easy on this. What's the integration of d theta? It goes to theta. So we're going to have 1/2 r squared theta evaluated. Alright, so evaluated at 2 pi to 0. And what am I getting this right? This is an equation for area. You know what I mean? Hey, let's go back to if I have an equation like this that says, hey, this is 1, and this is x, and this is y, and this is y is equal to 1. You know what I mean? If I integrate this, if I go integration of y 1 dx, and then I'm chopping this as dx, you know what I mean? Well, hell yeah, I'm just going to get I'm going to get a new equation, or I can say I get an area equation that's area is equal to x. Cool, and is that right? If I go over 1, my area, if this is 1 and that's 1, area is 1 times 1, that's 1. Alright, let's throw area at 2x, you know what I mean, 2. Well, cool, we get 2 times 1, area is 2. So this equation checks out. So hell yeah. So, you know, even though you have this technical thing of going, well, I'm going to evaluate from 2 pi to 0, and I know I go, you know, all I have to do is go 1/2, and then 2 pi, we're going to square that. No, holy hell. You know what I mean? This is my theta. So I'm going to go 1/2 r squared times 2 pi minus 1/2 r squared times 0. You know what I mean? Do the second minus the first. But if I just know that this is an equation for area, you know, I mean, I'm sorry. Obviously, this is and did we already mess up? I feel like we messed up, because how the hell did we get volume? You know what I mean? Shouldn't when we do this, this should be we should have meters cubed. I gotta pause. I gotta pause the video, because that seems like a huge error. Oh, nice. Hell yeah. You know what I mean? And this is perfect. You know what I mean? This is learning on the fly. Because if you can't pick out a mistake while you're doing this process, like if I can't pick out my mistake and fix it, then I don't have a fundamental understanding of what's going on. So obviously, yeah, this picture was a pretty good representation of a side view, but what the hell, what's the top view of this? It's a circle, obviously. So if we look down, basically we're taking a circle with a thickness ds. So my apologies, and we're gonna grab a fresh sheet of paper. So hell yeah. So let's get this. We got the sphere, and we're gonna go this way, and then we're gonna slice that, and hell yeah, there's our slice, and we're gonna do another one over there, and then, but if we take this, we're gonna get a full circle with a thickness ds. You know what I mean? Hell yeah, we have a radius, you know what I mean? You know, diameter or whatever. And so if we take the volume of this, well, what's the volume? It's going to be the area of a circle, which is pi r squared, and then volume is going to be pi r squared times ds. You know what I mean? And I have to go back to you know, the original. If we do have an angle in here, theta. Theta is in radians. Radians times radius is something normal. That's arc length. Now I can change it into d theta r is equal to ds. I'm totally comfortable now. You know what I mean? Even though this is a d, and you know, taking things to a tiny amount where they're insignificant and microscopic beyond, you know, recognition. That's why the d just destroys your mind. Anyway, but no, I fully understand that now. And so we can take this value of ds and shove it into there. So now we got volume. Oh, whoa. You know what I mean? Don't make the classic mistake. This is the area of this thing, but what we're trying to represent is just that slice. And then we're going to integrate it over that 2 pi, you know, theta radians. So the area of this slice is this volume divided by 4. So we're going to clean this up. We're going to go 1/4 pi r squared ds. So now we can throw the ds in, and we'll keep it real simple. 1/4 r squared, and then we got d theta r. So hell yeah, very obvious. We substitute that in for ds. Now we get the r cubed term. So we got 1/4 pi r cubed d theta. Now, cool. Now, you know, and don't get confused. you know, we already have our meters to the cubed. What we're just integrating is we are just like integration from theta, like theta's in radians. It's unitless, but when we add all these areas, hell yeah, after we do the integration, that's what we're going to get. We're going to get an addition of all those areas. You know what I mean? So it's not like taking, you know, this graph of y is equal to 1, integrating it, you know, I mean just taking this line of y is equal to 1, which only has one parameter distance, so let's say meters, that's the units, and then when we integrate, you know what I mean, with a dx, which is a microscopic distance, and you know, then you sum all the areas, then hell yeah, the integration of that is area, you know, with meters squared. But in our case, no, it's kind of different. We're just summing all those up. We're not taking this and then making it dimensionally align to a square. You know what I mean? We're not going from linear distance to an area. This, we're already taking a volume, and then we're just adding all the slices between 0 and 2 pi. So I'm glad, even just from my understanding, I'm glad I talked my way through that one. And so, hell yeah, we already divided by 4, and now we're ready to integrate, and this is our dv. So now, you know what I mean, there you go. So we got perfect equation. dv on that side, d theta, we can integrate dv, we get volume. Integrate this side, we get 1/4 pi r cubed, and now we get theta evaluated 0 to 2 pi. All that jazz about this is a volume equation, and so the volume at 2 pi is the volume, you know what I mean, because we're actually starting at 0. If we just wanted half, you know what I mean, or if we wanted the volume, check this out, you know what I mean, and now you can do cool things. Let's say I just want the volume of the bottom half. Then I want to use this, I want to find the area at pi and the area at 2 pi, and then I want to take this, subtracted that, you know what I mean, so that's where this comes in. If I want pi to 2 pi, you know what I mean, so that's kind of my talking through, like, what the hell does this even mean when you're evaluating at 2 different points? Well, we just said that this is an equation for the volume, you know, given any theta. Okay, cool. So we did it, and then so we're going to get 1/4 pi r cubed to pi, and I'll do it straight up, just like you would do r cubed times 0. Obviously, that's just 0. And here's our equation for volume of a sphere. Now, it's wrong, but let's do it. So we got the 2 comes over here. So we got 2 divided by 4. We got pi squared r cubed. And then we do know the volume of a sphere is 4/3 pi r cubed. So now, this term, we need to see if it's similar to that term. And the first way to do it is just kind of like the, you know, the feel it out method. Hey, this is 1/2 pi squared. What the hell is pi squared? It's 3.14 squared. That's about 10. So this thing's basically going to come out to be 5. And then no one ever actually does this. And you know, what is if you did cube the radius, what would you multiply by it to get the volume? Well, we have pi right here. It's basically 3, and then 3 divided by 3 is 4. So this kind of comes out to 4. So there you go. So just even right now, I have an understanding that, let's say this wasn't accurate, and it is bad integration. Well, this volume was just a little bit bigger. You know what I mean? And so from this representation, it's taking not a representative slice. It's not perfectly, you know what I mean? I guess from my perspective, it's not, it's like I'm taking too big of a slice, so maybe this is more like that, you know what I mean? Maybe something going on like that. This equation is just a little bit lower, you know what I mean? And so, so then I would have to change my equation to get that area right there. This area has got to be a little bit smaller. But you know what I mean. It's going to be a little bit bigger because 3 divided by 3 is 4, but this is 3.14. So we do have a little bit. So now let's check it out. So we got 4 pi divided by 3. So this number for sure is 1.188. Now this number over here is going to be, oh, and let's totally spell it out. So 1/2 pi squared radius cubed. You know what I mean? This is the bad integration style, but damn it did it help me learn definitely integration from this bad example. And maybe just because I got to own it, you know what I mean? It's like, hell yeah, I got to do it in a way that no one's done it. And so we got 0.5 pi squared, and oh, and this wasn't even 5, it was 4.934. You know what I mean? So we are definitely off. It's not good. But from my perspective, I was just like, hell yeah, it gets me in the ballpark. If I had no idea what this equation was, I am statistically closer to understanding the volume of a sphere compared to just saying, hey, maybe it's just a big cube with sides D, D, D. You know what I mean? Because if that was the case, then all these sides would be 2R, 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 and this would be 2R cubed, which would be 2 cubed R cubed. And we would have 2 cubed as this. And we would have 8. So that is horrible. You know what I mean? So right there, that's a horrible representation of the volume of a sphere, to just take a cube and then throw the sphere in the box and call the whole box the area. Alright, hell yeah, and I did say statistically, how do you figure out? Well, you have to take the right one. And I don't get too complex. I do kind of throw an absolute value up here, but you wanna take the right one, you know what I mean? Put it on the bottom, 4.188. Throw the right one, put it on the top, 4.188, and then just subtract the other one, you know what I mean? And 4.934. Always take the absolute value, because you can obviously then go back to be like, well, this is, you know, because we're just trying to find the percent error, the absolute, you know, the absolute value of the percent error. Like obviously the, yeah, I hope that makes sense to me even. So we got 4 divided by 3 times pi. I'm going to store that as x. And then this one, 0.5 pi squared. Whoa, 0.5 pi squared. I'm going to store that as alpha a. So I'm going to go x minus alpha a divided by x. And since that was a bad way to do it, I'm going to go alpha a minus x divided by divided by x. And then multiply by 100. And yeah, this is 17.8% off. You know what I mean? No bueno. But what about throwing it in a box? We can do the same thing. You know, 8 minus 4.18. And so that's going to be 8 minus x divided by x times 100. I mean, this crap is, this guesstimate was 91% error. You know what I mean? Where this, oh yeah, it's error. So this is what this gives. It's a percent error, which can be an absolute value. It's not a percent reduction. You know what I mean? It's not that. But it's a percent error equation. And so 17.8, you know what I mean? Like I said, not good, but it helps me, you know, figure out that integration process. Now, I might end the video right here, but I kind of wanted to, because the whole idea is like the actual way to figure out the volume of the sphere might be a magic trick. You know what I mean? It's just like, well, how did they do it? I do remember that they took surface areas, you know what I mean? And then you would take a surface area and you would take the surface area of a sphere, and even that we would know how. We would first have to figure out the integration on that. You know what I mean? So we can't use a bad integration approach. But to find the surface area of a sphere, what we're going to find is the area of a circle. 4. It's 4 of those. 4 times the area of one circle is the surface area of a sphere. So let's do it. Let's make a long video. So, and then once we find the surface area of a sphere, then we have to figure out, like, well, you know, how do you integrate? You know what I mean? Basically, you're going to have a radius. So we can know the surface area of this sphere because it's a radius. You know what I mean? Once we know the radius of that sphere, then we can find that. And then so our thing will be dr that will be integrating, and we'll be integrating from 0 to the radius. Okay, and then when we do that, we'll add up all the slices of these volumes, just like we did for d theta probably. Okay, so we have I have some idea potentially on how to do this, but the first is, holy Toledo, we have to come up with what's a what's a good representation on a slice of a how do you find the area of a sphere? Because I think I've already done this one like poorly, you know what I mean? Well, I would just slice it like this, and then say the slice for a half sphere, you know what I mean, it is literally just a triangle. You know what I mean? So there I have it, and it's going to be a triangle this way, and I can kind of do that same approach. Well, let's say it was a full rectangle, and then I know that this distance is it's a vertical circle, and then that this distance from there to there is half the circumference. I know circumference is 2 pi, and so I know that the half the circumference is just pi. So cool. So I know that this is 3.14. I know that my thickness is arc length. You know what I mean? We can't make that mistake. It's not d theta. It's an actual distance. It has to be, so ds. And we know that theta times radius is something normal, arc length, so d theta r is equal to ds. So now we're on a roll. And then I do know that this area of this is pi ds, but I need the area of this. And the diamond shape, I mean, just from hell yeah, this base is equal to that base. So you know what I mean. So this is half of that, and then this is half of that. So if I said that right, it's oh damn, is it just half? Because I thought it was a quarter. For whatever reason, I thought it was a quarter. Is it a quarter? Like my mind's melting right now. I guess it's just a half. Oh, I hope I don't bugger this, but I don't have any way to like determine. Well, let's do it this way. If it's a half, I know halfway. Like hell yeah, that's a half, understandably. So then yes, this way is a half. Going from here, there you go, because these two should equal that one. I think, you know what I mean. It feels like I'm not drawing the picture right, but we'll try it. We might be. So the actual one is divided by 2, so we have 1/2 pi. The ds is d theta r. So we're gonna have the area is 1/2 pi r d theta. But again, what am I missing? You know what I mean? Like, I'm making that same mistake. Checking my units, I only have meters here. I already should have area, and it's on this pi. Pi is just 3.14. Yeah, 3.14 what? So how did I? You know what I mean? I think I messed it up because circumference is pi d. You know what I mean? So there was my mistake. I just dropped the r. So here we go. So we have pi r. And now let's do it again. We have area is pi r times ds, and then we're going to divide that by 2. We're going to go 1/2 pi r. This ds is d theta r, and so we're going to go 1/2 pi r squared d theta. And now we're ready to rock and roll. We're going to integrate, and this is the area. But once we rock and roll this thing all the way around 2 pi degrees, you know what I mean, we'll just be set. So 0 to 2 pi, and we have 1/2 pi r squared d theta. Obviously, it's just 1/2 pi r squared theta evaluated at 2 pi. I'm going to take a little shortcut and just say, and this is area, this is surface area. So my surface area is 1/2 pi r squared 2 pi. And now I can say, oh, so yeah, I'm just doing horrible integration again. So obviously I'm doing bad integration, but yeah, I guess I don't know the magic trick on how to find the surface area. So this video is actually taking two horrible ways. That's exactly what I wanted. I wanted to do bad integration. I just wanted to make a video on not knowing the magic trick. Not knowing that, yes, these are not representative. You have a curved surface. These are not triangles. You know what I mean? If you have this, a flat pizza, hell yeah, these are triangles. You know what I mean? And the second you divvy them up, these are totally straight lines. These are friggin' curved lines. You know what I mean? The area will be less. So I think even just by that, I think we're gonna have an approximation that's too much, but we'll figure it out. So we have a surface area. The 2's kind of cancel, and we got pi squared again. Radius squared. And so we have pi squared. This is going to be 9.869 radius squared. And we even need to feel this one out because we know the surface area of a circle is just the area of a circle is pi r squared. That's the area of a circle, and we know the surface area is just 4 of those. It's just going to be 4 pi r squared. And don't quote me on that. I'm just like that's my knowledge. You know what I mean? If I'm lost on an island, that's what I'm going to remember, and I'm going to use as my axiom. It's like, hey, isn't a sphere? The area is just 4 of these circles. You know what I mean? For whatever reason. And so now we're going to say 4 pi. 4 pi is 12.56, and this is only 9.869. So this was undershooting it. So yeah, and that makes sense now to me. Is no, it doesn't. Oh no, I guess it does. It makes sense to me that these areas have to be bigger. So these areas would have looked like that. You know what I mean? And that's what we see. We get the orange peel effect when we do a world map. When we do a world map, it looks like an orange peel. It does not look like sharp triangles. Sharp triangles will undershoot it. And now we can figure out, I'm going to store the x as the actual, and this stored as alpha b. So now we're going to go alpha x minus alpha b divided by x times 100, and we have a 21.46% error. And so there you go. And so that was the surface area, and we're just going to use it. You know, I mean, we're going to take this bad integration, and we're going to say the area, surface area, is pi squared r squared. You know what I mean? And now we have to do the trick to figure out how to, you know, now we do kind of an inner sphere, and we take the surface area of that, and we say, hey, that's a distance r and a thickness dr. And so now we have to integrate, you know what I mean, integrate from 0 to r, and we need to figure out what that means, you know what I mean. So, and sometimes you can do like, no, I guess we'll stick with R. So the volume of this is going to be the volume of that little circle is going to be the surface area times the thickness. So you have the surface area times the thickness. That's dr. You know, as long as the thickness is super small, you know what I mean. It'll be the volume. Okay, so and then we got to that's dv, and then we got to integrate from r is 0 to r. Cool. So let's do it. So that should be really easy. We got pi squared. I mean, all we want to do is just the basics of being like, are we even doing the integration right? When we set it up, do we have do these match up? I mean, this is meters squared units, and then dr will be in meters. You know what I mean? So in this scenario, we're not integrating around a theta. So when we integrate, we'll get that extra meter term. So we'll have meters squared times meters, and we'll add up all those slices and we'll get volume. Okay, so this term is pi squared r squared. I just want to check that. Pi squared was 9.86. Cool. And then we're going to go dr. So now we're going to integrate from 0 to r. And cool. So we need to, what's the integral of r squared? Well, we go integral of r squared dr is going to be r to the 2 plus 1 divided by 2 plus 1. And I do this straight up because I swear you can mess it up. So we're going to go r to the 3 divided by 3, and now I'm just good to go. So when I come over here, the constant just comes out. It doesn't really matter, but we got pi squared, and we got this 1/3. 1/3 pi squared r, sorry, 1/3 pi, yeah, pi squared r to the 3rd evaluated from 0 to r. I apologize. You know, textbooks would probably say this is rho. You know what I mean? You know, it's not the radius of the circle. The radius of the circle is like that. That's your dimension r. But this, sometimes they'll do like a rho, and we'll do that. So you know what I mean? It might make a little more sense. So we have this dv is area of the sphere times d rho. You know what I mean? So now we're going to have area of the sphere is pi squared r, surface area of the sphere, pi squared r squared. Okay, now we're going to do d. Oh, no, yeah, I see. If you do this inner circle, the surface area of that will be pi squared pi squared rho squared, and then it'll be d rho. You know what I mean? D rho. It'll be that thickness. You can do it with r squared. You just need to know that your dimension r is r, you know, like r initial. You could be like r initial or r naught. So that might make more sense. Where this r is, yeah, it's all the same. It's all the same. But then when you go evaluate it, it makes sense. You know what I mean? But you could do this. You could do rho, and then you would have. So now we have. Now we do have a dv because we have the area of the sphere d rho. This is the volume of that sphere. Now we can integrate from 0 to r. You know what I mean? 0 to r naught. So there you go. And then when we do that, we integrate with rho, and we could say that rho squared plus 1 divided by, rho to the 2 plus 1 divided by 2 plus 1. That's the integral of that. It's going to be rho cubed, 1/3 rho cubed. So then we would get pi squared, 1/3 rho cubed, and we're going to integrate rho from 0 to r naught. You know what I mean? Our dimension. So that makes sense, and you throw that into rho. Cool. Now your volume of a sphere is 1/3 pi squared r naught cubed, and obviously in this scenario it's just, you know, r. So that's what we're going to have. We're going to have the volume of a sphere is 1/3 pi squared r cubed. But yet again, this is obviously the wrong volume of the sphere, and we'll probably have more error because we did the surface area wrong. But, you know, maybe something's come out in the wash. You never know. Maybe those errors could either multiply or they might cancel. So we're going to have 1/3. And what's the actual volume of the sphere? It's 4/3 pi r cubed. Let's see how we're doing. You know what I mean? Hey, this was about 4. This is 10. 10 divided by 3 is about 3. Okay, so this is going to be undershot. And if we go back to our original example, hey, this was overshot. So we had 1/2 pi squared r cubed. This was 4.934 as a multiple. The actual one was 4.188 as a multiple. And then let's throw this into our calculator. 1/3 times pi squared. And we get 3.289. You know what I mean? So overshot and undershot. So we're going to store that as alpha c, and we're going to go x is, well, let's get this, 4 divided by 3 times pi. Cool, stored as x. So now we're going to go x minus alpha c divided by x times 100%. And we have a percent error of this one of 21.4%. And we had a percent error of this one as 17.8%. So doing my first example wrong, hell yeah, you know, it was a fast way to get there. That was taking that slice, and we only had an error of 17.8%. The errors multiplied when we tried to take that vertical slice. Obviously, it's not. It's orange slices. It's not perfectly triangles. And I'm done. You know what I mean? Like, I'll probably sleep on this and be like, oh, yeah, no duh. No duh. Like, I know exactly, you know, what slices to take to find the surface area of a sphere. But that's the math trick. That's the puzzle. And I like having those puzzles later. Sometimes I just want to go for the answer, and sometimes I want that puzzle to be a mystery. Alright, so hell yeah, that's a video. Thanks for joining me. Alright, hell yeah. So I came up with one more thing, you know what I mean? There's a concept, you know what I mean, when guesstimating, if you can for sure guess high, and you know your answer is high, that gives you a piece of information. And if you can guess low and for sure know that you undershot your answer, then you can always add those two numbers and find the mean between them. Add those two numbers, divide by 2. So I just realized that we had, this is our exact answer, but this was undershot and overshot. So this is stored as alpha A, and then this is stored as alpha c. So we're going to go alpha a plus alpha c divided by 2. And guess what we get? We get 4.112. Very close to this. I'm going to store that as alpha d, and now we can, this is stored as alpha x. So I can do my percent error. I can go x minus d divided by x times 100%. And hell yeah, we got 1.8% error doing that. Now, I don't think there's any rhyme and reason for those to strategically cancel in any effective way. But just from the scenario that it's a cool guessing technique. If you can for sure find something about the problem where like you positively 100% know that you got a higher answer. And I think that's an incredible concept in math. And then also if you can for sure, hey, I know I undershot the answer and I understand why. Then you can add those and get to a mean, and it's just surprising. You know, that there's no, I can't imagine there's any calculus magic that makes this answer close. I think it's just happenstance. But yeah, it comes from the fact that you overshot and undershot, and at least you can aim for the mean. You know, and that's taking. Let's say you didn't know anything about this, but you never know. Like one of your answers, even if it was overshot, might be pretty darn close. It might have been way closer, and then the other one, undershot, could have been hella far away. And then so then in that case, adding them and then dividing by 2, the mean might, you know, even be worse than 1. But in this case, no, we were about evenly high and evenly low. But I'm going from the perspective that if you did not know the volume of a sphere, you would have to still have a check on reality that, you know, it's not, you might not be getting the mean, the middle point between these might not be any more accurate, because the answer could have fallen near one of those two things if you had no idea what the solution was. Okay, I think that was said halfway decent. But anyway, that's where I'm going to end it. Thanks for joining me, and that's a video.